Welcome to this lecture series in linear algebra. We're starting a new module, and this will be about a very interesting and important notion of dual spaces. So let's recall a few things that we need. So suppose V and W are vector spaces, and we have a basis for V and a basis for W. Then we can define a basis for this vector space, which is the space of all linear maps between V and W. So yeah, these vector spaces are over the same field, over a field F. Only then this makes sense. So we define Tij as, via this recipe. You can pause the video and take a look what this is, and we saw that this forms a basis for this space. All right, and we noticed that since it forms a basis, we saw that the dimension of the space is product of the dimension of the participating spaces. So that's one fact. And let us also recall a notation. This denotes the vector space of all polynomials over R, meaning the coefficients of the polynomials are real numbers, and the degree of each polynomial is at most n. So this was an n+1 dimensional real vector space. This can be done for any field, but we will just need it for the real number field. All right. These are two simple problems. I think this is just one problem. Yeah, this is just one very simple problem. And now let us get started. So fix a vector space over some field. Then a linear functional on V is defined as a linear map from V to F. So recall this can be thought of as a vector space over F, one dimensional, and any linear map of this sort is called a linear functional on V. Just a definition. The set of all the linear functionals on V is written as V star. So we just decorate the letter V with a star. And therefore, what is V star? V star is nothing but this vector space. It is all linear maps from V to F, so that it is this vector space. So V star, the set of all the linear functionals from V to, all the linear functionals on V is itself a vector space. And this is called the dual space of V. So that's a terminology. This is called the dual space of V. And note that dim V star is same as dim V because the dimension of this space is the product of the dimension of V and the dimension of F. Dimension of F is 1, and therefore dimension of V star is same as dimension of V. So just a notion. It's unclear why is this even useful, but we will get there. So now we can, given a basis of the vector space V, we can come up with a basis of the dual space. And that is something that we saw in the recall, because after all, what is the dual space? It is Hom V comma F. We have chosen a basis for this, and there is a very natural basis for this, namely the set which contains the identity of the field. And if you just use that and look at the recall, we can define elements of V star in the following way. So this is equal to 1 if I equals j and 0 otherwise. And this collection forms a basis of V star, and this is called the dual basis of the basis B. So every basis has a corresponding dual basis. Okay, so just think about what is going on here. There's not much going on once you know how we constructed a basis for this Hom V comma W, where we were given basis of V and W, then it's the same construction. There's nothing new happening. All right. So now let's look at an application of this notion of dual spaces. So first, let us recall a result that we proved earlier, which was called polynomial interpolation. So suppose we have n distinct elements of a field F and some n elements of the field F. Then there is a polynomial of degree at most n minus 1 over F, such that the polynomial evaluates to y1 up to yn on these values t1 up to tn. And we saw the geometric meaning of it. If suppose we were working on the real number field and we are given some, let's say 3 things, t1, t2, t3, n equals 3 here, then there is a quadratic polynomial which gives us the prescribed values on t1, t2, and t3. So those prescribed values could be anything. There is a at most quadratic. You could also have a linear polynomial if the values of y1 up to yn are chosen in a certain way, but in general, we'll get a quadratic polynomial. So that's what this is trying to say. You can interpolate these values using a polynomial. And also recall this notation. If you know about integration, you know what this is. If you don't know, then let me just think of this as a notation. So this just means that number. But yeah, the only way to really understand what's going on is to think of it as area under the curve. So consider the curve of x to the n. This is the curve for x to the n. If this is a and that is b, then this area, the area between the two values a and b and below the curve x to the n is what that is, and it can be calculated via this formula. All right, and now what we want to prove is the following result called the quadrature formula. Fix two real numbers a and b, and suppose we have n distinct real numbers between them, and they are in order. Then we want to show that there exist some n real numbers such that the integral of a polynomial of degree at most n minus 1 can be calculated like this. So once and for all, you can find n things, n real numbers, such that this kind of linear formula just calculates these integrals, where p is a polynomial of degree at most n minus 1. So it's a result. I don't know if this is very useful or where is it used, I don't know, but I just mean to give an exposition of or illustration of the notion of dual spaces. So that is how I approach this. And let's see how we prove this using the notion of dual spaces. So first we define a function I. It picks a polynomial of degree at most n minus 1 over r and produces a real number, and it is just the integral. So I of p is the integral of p from a to b. So that's the definition. And thus, I mean, just note that it is a linear map. That this belongs to the dual of this vector space. So linearity can be easily checked. Okay. Also, for each element of Rn, define a map phi sub x, again from the space of all polynomials of degree at most n minus 1 to R as phi x of p is x1 p t1 plus dot 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 xn p tn. Again, just some definition, and one can note that this is also a member of the dual of this vector space, meaning it is linear. So now what the problem asks us to show is that we want to show that I is equal to phi x for some x. This is exactly what the problem states, or this theorem states. Okay, so once we convince ourselves that this is what we want to prove, we can go ahead. Right, so to do that, define a map T from Rn to the dual of R vector space as Tx equals phi x, phi sub x. And again, recasting the problem is want to show that I is in the image of T. So yeah, before I state that, I mean, it makes sense without any further comment, but note that T is also linear. So this is what we want to show, and we'll exploit the linearity of T. And we will show that T is surjective, which will prove what we want. So we will show that T is surjective. Once we show T is surjective, obviously I will be in the image of T, because I is after all a member in the target of T. And since these two vector spaces have the same dimension, this has dimension n, this has dimension n, and therefore this also has dimension n. So we will actually show that T is injective, because that is equivalent to surjectivity of T, because these two spaces have the same dimension and T is linear. So injectivity of T is the final goal now. And how do we do that? All right, so let something be in the kernel of T. Then Tx, which is equal to phi x, is the zero map, which means what? Which means, thus phi x of P is 0 for all P, which implies x1 pt1 plus dot 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 xn ptn equals 0 for all polynomials. But now we can use polynomial interpolation by polynomial interpolation, the result that we stated. For each I, there is a polynomial pi in the space such that pi on tj takes the value 1 if I equals j and 0 otherwise. So that's immediate from polynomial interpolation. And now since phi x of pi is 0, because phi x of any polynomial of degree at most n minus 1 is 0, we get that xi is 0. Right? Because once you substitute pi here, this expression has only one term surviving, which is the ith term, and that is xi, which shows xi is equal to 0, and therefore, since I was arbitrary, xi is 0 for all I, and thus x is 0. X was arbitrarily chosen in the kernel. So what we have shown is that kernel of T is the trivial thing, which implies T is injective, and this is what we wanted. So that's it. So a nice application of the notion of dual spaces. And with this, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.